Ladies and gentlemen, good morning and good afternoon, and welcome to our last webinar titled Enabling the Integration of Low Temperature Renewable Energy Sources into District Heating and Cooling Networks. This webinar is part of a series that is being conducted by IRENA, and it's part of a project that is being done in collaboration with the Aalborg University and in the framework of the Global Geothermal Alliance. This project is supported by the government of Germany through the International Climate Initiative, IKI. My name is Jack Kiruja. During this webinar, you have an option to listen either through your computer by selecting the mic and the speaker option, or you can choose to listen by telephone by selecting the telephone option and then entering the phone number and the PIN that will appear on your screen. In case you experience any technical difficulties, please do not hesitate to contact our GoToWebinar help desk on the number that is showed on your screen. During the webinar, we encourage all the participants to participate actively by asking questions. And this you can do by typing in your question on the question pane. At the end of the webinar, we'd also like to have your feedback on what you think about the webinar. You can do this by filling in the survey that will appear when you end the webinar application. In case you'd like to watch this webinar again, or you would want to share it with other people, we're going to make a recording available on the IRENA YouTube channel, as well as on the website of the Global Geothermal Alliance. The slides that will be used in today's presentation will also be shared with the participants. Now, this series is made up of 3 webinars. In today's webinar, we are going to look at how to overcome the challenges of integrating low temperature renewable energy sources into existing district energy networks and buildings. In our previous 2 webinars, we looked at the following. One was on strategic heating and cooling planning for district energy systems that are run on low temperature renewable energy sources. And 2, we also looked at the enabling frameworks for district heating and cooling that will enable the development of the district heating and cooling systems. The agenda for today's webinar is that we are going to have 4 presentations. And these presentations will be divided into 2 parts. In the first part, we are going to have the Aalborg University giving us the scene setting presentation, which will be followed by a presentation from IRENA, and then we're going to have a question and answer session. In the second part, we'll have a presentation from ENGIE, focusing on district cooling, and this will be followed by a presentation from the Iceland Renewable Energy Cluster, focusing on the geothermal and energy market in Iceland. This will also be followed by a question and answer session. And we encourage all participants to participate actively by sending in their questions, and where possible, indicate the panelists who you would want to respond to your question. Now, these are the panelists for today who will be speaking, giving us the presentations on the different aspects of this topic. And to begin as of, we're going to have the first presentation. The first speaker for today will be Mr. Gurbuz Gonul, who is the Director for Country Engagement and Partnerships at IRENA, and is going to give us his opening remarks. So, Mr. Gonul, yes.
Thank you very much, Jack. Ladies and gentlemen, I would like to welcome you all to the last episode of the series of IRENA webinars on low temperature renewable energy solutions for the district heating and cooling systems. The webinar is being organized in collaboration with the Aalborg University under the umbrella of the Global Geothermal Alliance. The objective of this series of webinars, and more broadly of IRENA's work on the topic, is to raise the understanding of local and national policymakers on viable options and associated tools available to facilitate fuel switch to renewable energy in cities through modern and efficient district heating and cooling networks. This work is undertaken in the framework of the Energy Solutions for Cities of the Future project. Jack already mentioned it, but at this point, I would like to thank once again to the government of Germany for their generous support to this project through the IKI program. Jack also mentioned about the first two webinars. The first one was held, I think, more than a month ago. It was 20th of April, which looked into how effective strategic plans for district heating and cooling can be developed through a coordinated approach of taking into consideration the interplay between heat supply, heat demand, and improving energy efficiency. Recognizing the need for establishing a conducive environment for district energy investments, the second webinar was organized 2 weeks ago, which highlighted the enabling framework conditions, including the necessary regulatory and policy environment financing options, which have all been successfully employed in different contexts to realize successful projects. And now today, we will dive into technical solutions to the challenges for integrating such renewable energy solutions into district heating networks and buildings. Ladies and gentlemen, most of the heating and cooling today is generated by fossil fuels, resulting in pollution and carbon emissions, as well as the associated health and climate change concerns. As the world population increases and the rate of urbanization grows, the situation could deteriorate further if urgent measures are not taken now. Fortunately, the use of locally available renewable energy sources has proven to be both technically and financially viable to reduce carbon emissions in the heating and cooling sector. And what we have seen is the numbers are very encouraging. Almost 72% of the newly installed power projects last year were renewable energy based. And we believe that renewables have vast potential to play a more significant role in the heating and cooling sectors too. Projections indicate that as much as 77% of energy for heating and cooling could be supplied from renewables by 2050, up from only 8% today. In this regard, we believe that the guidebook of best practice that we have been working on for a little while as part of this project, but now it is close to finalization. I think this guidebook is going to offer a useful tool in raising awareness and providing guidance to policymakers at both national and local levels on the available technically and financially feasible options for penetrating higher shares of renewables into heating and cooling networks. As I said, we are currently finalizing the guidebook together with Aalborg University, but also we have been consulting a group of practitioners formed mainly from the members and partners of the Global Geothermal Alliance, but also some other experts also participated in that group, and they have provided very valuable suggestions and comments in developing that guidebook. And this guidebook will also be the basis for our future capacity building activities, and we will make available the publicly that guidebook once it's published. We plan to undertake a series of regional capacity building activities where we see transformative potential for utilizing renewables for heating and cooling in different regions. In fact, the first capacity building event already took place back in December. That was focusing on Southeast Europe, and the event took place in Serbia, Belgrade, Serbia. And now we are planning the second one in the coming months. Obviously, we're planning it in China, and it will cover China, Mongolia, and a few other countries. But we will be only able to hold this event once the current pandemic situation improves. In this regard, we very much welcome collaboration with like-minded partners in the organization of such capacity building activities in other regions, like in Central Asia, Eastern Europe, Latin America, and also MENA region, Middle East and North Africa region. And today, I very much look forward to a fruitful discussion and your active participation in the webinar. Thank you very much.
Thank you very much, Mr. Gonul, for that wonderful opening remarks. And as you've mentioned, we are working on the guidebook, and part of what the guidebook will be presenting is how policymakers can be able to develop district energy networks in their areas. And the guidebook will be focusing on 4 key areas. The first one will be on strategic heating and cooling planning at the national and local level. And this part will focus on the mapping and assessment of the renewable energy resources that are available within the local authorities and within the national authority jurisdictions, and also how to match these sources with the demand for heating and cooling. And this was the focus of our first webinar. The guidebook is also going to focus on the enabling framework conditions that will facilitate the development of district heating and cooling systems, such as financing, regulations, and ownership structures. And this was the focus of our second webinar. It will also focus on the technical challenges and solutions at the network and building level, as well as the technical challenges that are inherent for each of the sources of renewable energy. And this is the focus of our today's webinar. Now, this diagram represents the ideal district energy system of the future that is going to be composed of distributed sources of energy for heating and cooling, including from renewables, from waste heat, which can be gotten from cooling operations in data centers and also in large commercial buildings like supermarkets. It will also include supply of energy from surplus energy from waste to energy power plants and from cogeneration, and also energy that will be obtained from heat storage facilities. This energy is going to be used for heating and cooling in the buildings that exist today, as well as the buildings that will be built in the future. And the energy will be supplied using a network of transmission and distribution lines. However, we have a challenge of incompatibility between the renewable energy sources that are available locally and the existing buildings and networks. And this incompatibility is as a result of the fact that most of the locally available renewable energy sources are low temperature, but at the same time, the existing buildings and the existing networks were not designed to operate with these low temperatures for heat supply. Apart from that, we also have inherent characteristics of these sources of renewable energy that make them that present challenges in the utilization. For example, in solar, we have intermittency of supply, and also it's a seasonal, it's an energy source that is available during some seasons and not others. When you look at a source like geothermal, it also has challenges like declines over time, and also there's a challenge of scaling and corrosion. And we are going to see in the next presentations how some of these challenges and others can be addressed from a technical perspective. And to take us through this part, we're going to have Professor Brian Van Matheson and Jacob Zink Thulefson from Aalborg University, who are going to give a presentation on the technical challenges and solutions for the integration of low-grade heat sources into existing networks and buildings. Professor Matheson is a professor of energy and planning and renewable energy systems at Aalborg University, and is also a leading researcher behind the concept of smart energy systems. Jacob Thulefson is an assistant professor in the Energy and Planning and Energy System Modeling at Aalborg University. And it focuses on modeling and analysis of energy systems to assess the consequences of using 100% renewable energy in the cities. So at this moment, I would like to give the floor to both Professor Mathisen and Mr. Thelifson to take us through the next session.
Thank you very much, and thank you for inviting us to be part of this project and this third webinar in our collaboration. Today we're going to talk about the technical challenges and solutions for low-grade heat sources into existing district heating networks, but also into new networks. In order to understand the context of heat networks, we need to understand also the building and those demands that we have. And we have divided those issues into three. We talk about the thermal performance of buildings, where we see it is extremely important to make energy savings and energy renovation of the existing building stock. And this is important, and maybe even more important than new buildings. We need to renovate the worst buildings first. We need to make sure that renovations are done when energy renovations are done, when renovations are done in general. And renovations are important when we look at the supply system. In the supply system, which we're talking about today, we see that district heating is a viable and cost-effective option that has a synergy with energy efficiency houses in the thermal and a good thermal performance of the building. We see that a district heating system can enable a number of new sources being pulled in to the grid and to the energy system. And we see that this kind of solution is more flexible and more cost effective than, for example, individual heat pumps or micro CHP or biomass boilers. We also have a third element, which is the building operation and user behavior. And of course, if we have a building that has a good thermal performance, we also need to have a good building operation and user behavior. In the future, we see a transition towards a smart energy system. And in a smart energy system, we don't see that a passive house or net zero emission buildings are standalone energy systems. They are part of an overall energy system. And when we look at buildings and thermal grids, we see it as part of a transform system where we have a backbone of electricity supply from wind power and PV, where we have created thermal grids that can integrate waste heat options, but can also integrate wind power via large-scale heat pumps that we will be talking about as well today. In such systems, we have integrated thermal storages on a larger scale, which are able to store energy when we have a lot of renewables, either from waste heat or from heat pumps and wind turbines, and which can be used then at times where we have lower amounts of renewable heat and operation of heat pumps. In such a system, we see a synergy between a well-insulated building and the overall performance of the energy system. Today we have an agenda where we will start by talking a bit about the status on district heating and low temperature district heating. Will then be coming up where we talk about technical aspects and the utilization of renewable heat sources. And then we have a case where we demonstrate low temperature heat sources and smart energy in the case of Aalborg. And now my colleague Jakob will take over.
All right, thank you, Brian. Yes, so I will go through these different aspects. I'll start on the overall aspect on district heating, how it looks, and then at least from a European perspective, and then I would like to go to some of the low temperature district heating options we have, also utilizing renewable sources, and then we have applied those principles in the case of Aalborg here in Denmark, where we integrated with the smart energy concept that Brian also just mentioned. Yeah, so what's the status on district heating in Europe? We have through various studies in Heat Roadmap Europe and other colleagues also at other universities have tried to get an overview of how much district heating we have. So in 2012, you can see that in some countries, quite many had access to district heating. If you take Denmark, Iceland, Sweden, and so on, we are in Latvia, Lithuania, so the Baltic countries, and in the Scandinavian, over 50% have access to district heating, but in other countries there's quite not so much access to district heating. So this is of course something that's worth looking into, also because when we go through our studies and analysis we make, that there's a huge potential for utilizing district heating also in the future renewable energy system. So you can see district heating systems exist in a lot of cities in Europe, but you can say they don't always cover the heat demand of people, but also exist for industry and small areas where they have them combined. So one of the key examples that we like to also promote is, for instance, that London in the UK is one of the cities where you could potentially benefit the most from district heating. But when we look at United Kingdom over here, there's very little district heating overall in that country. But in how many people live in on how many square meters, it's a very dense city. So you could potentially have a lot of district heating here, providing cheap and potentially renewable energy to heating to the citizens. So also going through the Heat Roadmap Europe 1 and 2, we focused on the 27 European countries back then, EU countries together, and then we have in the latest studies we've been doing, we've been focusing more on individual countries, both in the Heat Roadmap Europe 3 and the latest Heat Roadmap Europe 4. And in the Heat Roadmap Europe 4, we've tried to identify district heating potentials in the 14 biggest heating and cooling demand countries in the EU. Those are the one also showed in the figure. And you can see that in many of those countries, it's potential. You can potentially increase the percent of heat demand supplied by district heating compared to today. And then, of course, there's the white dot indicate our recommended level, but you can say there's an uncertainty depending on cost assumptions and so on that might land you different places. But in all cases, district heating can potentially be a solution compared to what it is today, or what we foresee in a 2050 scenario. So what is district heating? When we say that, maybe that's good also just to clear up, and also when we talk about different kind of generations of district heating. So what we call first generation district heating is based on steam, very high temperature underground, predominantly used in systems before 1930. High losses is a characteristic here, so this is one of the reasons why you want to try and lower the temperature, and that's also what happens when we go through the generation. You would see that the temperature of the heating medium, so in this case steam, is lowered. And but one of the advantages, of course, of having steam in your system is that with that high temperature, you could use it for industrial processes potentially. But as we will show this also, but this is not, of course, always the preferred option if you want to simply heat the room temperature and then hot water consumption for houses. So when we go to the second generation of systems, we're going to the kind of systems that typically were built between the 1930s and 1980s. It still remains in parts of the current water-based system. So this is water-based. So now we pressurize water, so it's over 100 degrees, but we have it as liquid water instead of as steam, and we transport it around. And in many cases, so we get some of the same issues in terms of when we have high temperatures, we have higher losses in the system, and also we need to use energy to pressurize it. So what we have in most of the Scandinavian systems, also where you can see it was over 50% in both, also in Finland and in Denmark and Sweden. And here we try and lower the temperature is lower to be below 100 degrees. So typically it's between 70 and 95 degrees in supply temperature. And then, of course, you want to achieve the lowest return temperature to the plant from the consumer as we can. So this is the current system in most Scandinavian systems. And of course, again, we try and minimize losses by doing this, but also supplying a high enough temperature that it's useful at the user, both for room temperature, for heating the room, but that's okay, but also for supplying hot water consumption and doing it at a level that's high enough to avoid any bacteria issues. And also with having 70 to 95 degrees, then we can supply a high enough temperature at the end of the grid to the consumer. And then we want to move towards this fourth generation district heating. So as you can see, we've been going through first, second, and third. So here we had steam systems, very high supply temperature, over 200 degrees, and then we lower the return temperature to be a little less than 80. And you can see now we go 100 in number 2, and here we can certainly use a little more resources. So we have some industry surplus energy. We can maybe use some large-scale solar. But now going into third generation and also fourth generation, we can start using more and more waste heat sources and other renewable energy. So if you want to move into using renewable energy in your heating system, it becomes a key component to try and lower the return temperature or the supply temperature as much as we can, because these sources typically produce heat at a low temperature. So one option is, of course, we can boost them with heat pumps if needed, but by having it lower, we gain access to many more renewable sources. In a current third generation setup, we can use data center heating, we can use heat from large solar panels, we can use excess heat from industry. We have the chance to have PV, wave, wind surplus electricity through a heat pump. But all these, or many of these, would require a boosting using heat pump technology. Whereas if we go to the fourth generation district heating, in some cases we will not have to do with the we don't need a heat pump all the time to supply the heat we need. So why do we want to go to this low temperature fourth generation district heating? We also investigated that in a research project called 4DH, and you can also access it on the website here. But we want to utilize more of the energy that is in our waste heat sources and our renewable energy. So, and we do this by enabling the use of low temperature renewable sources. And then, of course, to implement this, we have to have the right institutional framework. We need to have the right waste heat recycling. So we need to identify the right technologies. We need to integrate it with renewable heat, find the right mix between waste heat and renewable energy. We want to integrate low energy space heating and systems into the building. So we need to focus on the buildings and on the cooling systems to make sure that they are scaled in the right way to do these technology changes to fourth generation district heating. We want the grid to be configured right, and we want to have it to operate within the whole energy system. So this is not only a reason to do an efficient district heating system, this is also to do an efficient energy system where we take into account the best usage for renewable energy across the system. So what do we need to do to transition into this low temperature district heating? So we need to design proper design the networks and the consumer connections. This means that we have to have the right sizes of pipes, and we need to make sure that the right connections are to the buildings. So we have the right heat exchangers, we have the right capacities on the pipes going into connections going into the consumers. Because we are lowering the supply temperature to as much as we can, the difference you can say between a supply and return temperature changes. So the delta T between those two will become smaller potentially, because there's a lower limit to how much we can cool the water. So that is very important to have focus on not only supplying water but also cooling the water. But because of this lower delta T, then there's a chance that we might need bigger pipes, or we need the right pipes to support the flow. So this is why the buildings also need to be compatible, because the current infrastructure in many buildings, and maybe potentially also in many pipes, is designed for a different supply and return temperature than what can be achieved. So we cannot it's maybe not possible to get the right flow to the building. So we need to do investments into our building stock. We also need to look at potentially do renovations and energy efficiency energy efficiency changes into the to the building stock, so we can have the right heating consumption. Also, we have existing district heating systems. Where we can do this is we need to adapt the installations and potentially, as I said, retrofit buildings. In the new development areas and with new district heating systems, which can be relevant in many cases, it is possible to lower to design the system right away to do this. So meaning you can have low energy buildings and build them in the right way. You can have low temperature district heating already from the get-go, and by designing this, you are able to achieve a very efficient energy system in a local or a new development area in the new district heating system. And here this can be especially suitable because you are able to design it from the get-go. Also, one of the issues that some people mention is that district heating is not viable in a low temperature building or in a new low energy building, because we don't need so much heating. But this can actually be made more relevant with having low temperature district heating, because then the whole system is scaled better to new design standards for low energy buildings. And this is also what Brian mentions, that there's a lot of synergy between energy efficiencies and district heating. So if we look at the existing building stock, when we have space heating, so this is one part of what we want to supply with the low temperature district heating, we can have, there's a risk we have poorly insulated buildings and they require more energy. And right now our current system might not be scaled for low temperature district heating, so we need to do some equipment changes. We need to renovate the building stock. And I think it's a combination, we probably need to do both. And also we can introduce some, in other cases, in some countries, we don't really have user-controlled temperature measures, but this can be another way to do it, is that to allow the users to have thermostatic valves so they can control the comfort levels in the building. Is also relevant, so it's it also becomes upgraded. But by having these more efficient, by looking at renovating and by looking at getting the right equipment changes into the system, then we can also in current existing building stock very simply integrate this low temperature district heating. But of course this requires investments not only in the district heating system but in the buildings as well. One of the risks when you have a domestic hot water that you want to supply is that by lowering temperature you can lead to Legionella and bacteria growth in the water tank. So here you want to make sure you have a plate heat exchanger, which can be a solution to having with having a too low temperature in your hot water supply. When we look at the network, then low temperature, as I mentioned, can lead to higher flow rates. Low supply temperature requires that the return temperature is lower too. But as you can see, if we lower, this could be an example from the figure before. If we have a current third generation system, you might be very good and achieve an 80-degree supply temperature and a 40-degree return temperature. Now you lower it to the return temperature or the supply temperature to 50 degrees, and your return temperature is lower to 20 degrees. There's you can say a limit at some point to how cold it can be, and normally it cannot be colder than the heating, you can say, at the building site. So this is one of the lowest. We can maybe be a little colder, but it's very hard to get it too cold than this. So here you can see we're very good at it, but we still have now a higher temperature where before the temperature difference was 40, now it's only 30. So this means that we we could lead to higher flow rates by doing this. So we need to make sure we have the right grids that can supply having more water running through it. Also, when we look at the network, then we might need to build some new network. Simply now we get access to new excess heat sources. So that is also something we need to take into account. That we might need to build this. And then finally, it could become relevant to boost technology. So when you have a large boosting technology to implement those, so that could be heat pumps, for instance. And this is simply to raise temperature from the supply source, or because it is simply supply at a too low temperature, but we now have access to it and it's much cheaper to raise to 50 degrees compared to 80 degrees. Or it could be that we have such a low supply temperature that our grid is so big that we need to expand it to the system. So we have a heat pump or boiler or something placed in a strategic place, so we maintain our 50-degree supply temperature and it doesn't become too low to be useful for our citizens. So one way to do this is heat pumps, and we can use these large-scale heat pumps in our district heating and cooling system. They can support both heating and cooling. And one of the points, as I mentioned, is that we can boost these low temperature sources it could potentially be a data center, or if we have water from a lake or river that is consistent enough and where we can have a good enough flow, then we can also, or deep enough that we have stable water. so it doesn't freeze, then we can use that as well to boost those temperatures into to heating. And this is one of the advantages of using a heat pump in a district heating system, is that now we can connect it to some bigger heat storage or heat source, compared to when we do it at your own household. Then there's a risk that you might only do a air to water or air to air heat pump, which is also completely fine, but we will have more over the time. It would be a little more electricity heavy, potentially, because we use an ambient source that can be colder than it is possible to achieve in district heating system. So when we want to integrate renewable energy, two options besides having wind and PV to a heat pump is that we can use geothermal is an option, where we can utilize the heat either directly through heat pumps or through heat pumps if we do it as a shallow drilling, where we don't get the temperature high enough to go directly into the grid. Then it's possible to boost it through heat pumps. So again, here it's an advantage if you have a lower temperature for supply, or you can go deeper, or you have an extremely resource of heat, of geothermal heat that is both shallow and high temperature. Then you can also, of course, get that directly into the network. Look at it globally, then most resources are typically low to medium temperature, so could require a heat pump to be sufficient. Another option is solar thermal. Obviously, here we have the risk that this is seasonal by nature, meaning that it's most of the solar thermal energy comes in the summer, and you most of the time need your hot water and heating mostly in the winter. So here there's also a potential for large thermal storages. And one of the other risks maybe of solar thermal, you need the space to build it. So as you can see here, there's one from Silkeborg in Denmark, and they have built quite a lot of. It requires quite a lot of land to build these solar thermal plants. So this is also an option, of course. And one of the main thing here is that there is also enough sun in a country like Denmark, where it's mostly gray and rainy, to actually build these kind of technologies. And it's it's very relevant, you can say, in many places. If it's relevant in Denmark, it can be relevant in many countries that has a heating demand. So when we want to get these renewable energy sources into our system, it's relevant to use different kind of storages. And just to mention a few of those, we can have a borehole thermal storage, where we have small boreholes that we can access. We can have a mine where we drill a mine, and we have a heat storage, both seasonal, low, or we can have we can use underwater water reservoirs for storages, and then we can use a tank thermal storage, either underground or overground. And for these, for some of these, they are more seasonal storages, where you can have long-term seasonal storage, like the borehole thermal storage, or we can have a tank thermal storage, which can be more day-to-day. One that I have not mentioned here, but it's very common in Denmark, and it's also situated around this case here, is simply just a pit level storage, where you drill a hole in the ground and you insulate the hole, and then you fill it up with water. So it's very simple, cheap technology also to implement, and probably cheaper for now than many of these options also. So now I would like to move on into how we looked at 4th generation district heating in this Smart Energy Aalborg energy vision, where the goal was to transition Aalborg to 100% renewable energy, and we wanted to utilize efficient renewable heating in a low temperature system. So these principles that Brian and I just talked about, we wanted to implement them in a concrete city, in a plan for how they can use this to become 100% renewable. So currently the system in Aalborg is a 3rd generation district heating system, and we want to move into 4th generation. So as you can see, this is a Sankey diagram of how Aalborg looks currently, where we have coal and oil as the primary resource, a little waste, and some renewable, but not a lot. And the coal is primarily fueling a CHP plant, and the oil is primarily for industry and transport, alongside some gas also for industry. The oil is primarily for transport. So transitioning this into renewable energy, as a principle, we said we cannot do this in a way that limits other cities, countries, municipalities to also transition to renewable energy. So we made sure that we limit our biomass use. We wanted to make sure our transport reflects not only the local transport demand, but also global transportation from Danish and Aalborg population. And we wanted to define that the industrial demands locally were reflected in the inhabitants, so we don't have any you can have a very skewed system if you have a big industry located in a small city. So we wanted to eliminate that, but also scaling the industrial demand. So one of the first thing is that we had a key part was to include the low temperature district heating. This allowed us to have better efficiencies in heat pumps. It allowed us to lower the losses in the district heating grid. However, it required that we did investments and energy savings in buildings and in equipment in buildings. So when we looked at retrofitting the buildings, we went and made a specific analysis showing that there is a cost optimum between supply, which is the green line, and savings, which is the blue line here, where you can find a certain energy level in the district heating area where it makes sense to do savings too, else it becomes too expensive. And you can see over here that primarily we went into these, we had these 7 levels of saving steps, where these are basic renovations, and then these become new windows, new cavity wall insulation in level 2, new windows in level 3, and then actually first level 4, 5, and 6 is extra renewable extra savings. And you can see that predominantly we gain most of our energy savings from renovating buildings from before 1972. This is the main, so this big chunk, and this is the same for all the levels, that these are the main issues we have, where we need to do a lot in the retrofitting of buildings, and that will get us a long way. We have industrial waste heat also here, just to show we have a lot of new sources. And one key point to make of this slide is that we have a cement industry that currently supplies 20% of the heat demand in Aalborg. Just by lowering the 65 degree, we are able to go from 300 terajoules from them to 500 terajoules of energy. In total, all this will increase potentially from 1200 terajoules to 1300 terajoules. We utilize 100 megawatts of thermal capacity on heat pumps. These can be seawater in our case, or we can use geothermal resources. And then we have some heat pumps running on waste heat from industry, and we utilize a 40 gigawatt hour seasonal storage. And then we achieve this 100% renewable Smart Energy Aalborg. Just a quick summary. If we have no low temperature district heating, we see that our system becomes expensive, especially if we don't do any savings, we gain a more expensive system. If we have no excess heat from Aalborg, we also gain no excess heat, and especially if we don't do district heating, and we want to do individual heat pumps and everywhere, we gain a very, very expensive system compared to this vision system we made. So there are costs, not only efficiency savings and making it easier to do a renewable system, it also makes it cheaper to do it. So summary, it's technically possible to do this. It gives both technically and also socioeconomic benefits, but this requires planning, as this is not only something you do as a supplier, you also need to involve yourself in the building and in the building mass of the system. Thank you.
Thank you very much, Jakob, for that presentation. So we'll go to the next presentation, and this presentation will be given by Mr. Yong Chen. Mr. Chen is a program officer in IRENA in the Sustainable Urban Energy Program. And his work focuses on integrating renewable energy in buildings and in district energy networks, as well as in developing sustainable urban energy strategies. And his presentation for today will be focusing on the integration of renewable energy for thermal use in the cities, where he'll be looking at the technology, the project development, and case studies. So, Mr. Chen, we give you the floor to give us your presentation.
Thank you, Jack. Okay, I'm sharing my screen. You see it, all right, Jack, everyone? Hello?
Yes, we see it.
Okay,
I
good.
see it, yes.
Okay, good, thank you. And it's a great pleasure actually for me to join this panel and talk about work we have doing and at the IRENA in this sector. And I think the professors and from Aalborg University did a great job actually to give a comprehensive history and also the system about the district heating and cooling and why it's so important. Before I get into my topic, and please allow me to spend a couple minutes to actually broaden a little bit of context, for better understanding, for why we're doing what we are doing right now. I think probably as most of you know, this is currently in the world, this is about 67 to 76% of the global total final energy consumption actually for cities, and contributing to the roughly around 72% of CO2 emission currently. This is an important message, but this is not important enough for us to understand actually what's going to happen in the future. So over the next 30 years, there's 2.5 billion people moving to becoming the urban dwellers. So what does that mean? It means that over the 2 hours of the webinar today, there's going to be 20,000 people become the urban population. So how are we going to provide energy and for them to grow and to live? So this is a very important question. So this question only can be answered by today. That can ensure that such infrastructure be available for the tomorrow. So I think there's another message I think is very important to keep in mind, and it's 90% of those population increment will come from Asia and Africa. So that's the knowledge we discussed today and we shared, and actually need to be and effectively transferred to the other countries and broaden the applications. So that's otherwise impact will be very much limited. So that's very important for us to discuss and also to disseminate the information. And for example, like Iceland, the UN Geothermal Universities trained a lot of students from different countries. So this is just one example. So the GGA's or networks is also this is one of the platform we can use. So that's to keep in mind just there are broaden context and for the discussion we have today. Okay, and having said that, let me to get into the topic. And today I'm talking about how integration renewable energy and for thermal use in cities. So I will cover technology, and also thanks to actually Aalborg University that's already touched upon quite a bit on this topic. Probably going to save a lot of my time, and also project development and how I could develop district heating and cooling project networks, and also the production units and plants using renewables, and also share with two case studies briefly, and to just illustrate, what can be done at the city level in reality. And maybe I think it's important for us to have a look, what we mean when we talk about urban energy systems. And this is it's not a new concept, but different people have different understanding. So without actually having such debate, I would just highlight a few key factors that's important. And one first is it's a network. infrastructure. So it's actually in the cities or the energy system infrastructure, and is not standing alone. It's connected with other urban functions, and like waste management and systems, collection, treatment, and as well as the water supplies. That's just two examples I can give. And also the second have to keep in mind, this is a spatial temporal, and especially when it comes to renewables. And this is a granular data, and the granular actually scales. That's what we're talking about, rather than compared to the national energy systems. And it's also connecting to peoples. The people is very important too, the social dimensions. And that's how I interact with the technical systems, like energy is very important, because if there's a public acceptance, it's also one of the barrier actually in some cases actually to hamper the integration of a renewable. So the education and the raise the awareness to the urban population is also very important. So it has to be also scalable, because city is not cast in stone. This is always changing, evolving, and expanding, and in some cases even shrinking. This is so it need to be actually scalable, and upwards and downwards too. And trade-off options, and there's are many as well. So it's not only with the energy options, with also the demand side management response. There's many other options, and the cycle coupling is creating another domain actually where the trade-off options could occur. So this is also a very important, becoming actually more important factor to keep in mind. And it's vulnerable, and in terms of climate change, and we see this is the impact of climate change at the local level, at city level, has been widespread, as we can see from many cases you can read from headlines. And also this is so this is basically the cities. We can, from building level, we talk about energy, to the district level, and also to the urban, and also the entire city scale, including connected with other cities. And second, I will say, just a quick, actually, renewables currently is only contributing 20% urban energy consumptions, and mostly from to the building directly use. And the geothermal, we talk about the biomass, and it's another case. And the transportations, 1/3 of the energy consumption actually goes to the transportations. Mainly it's biofuels, and gradually, increasingly, and EVs, if provided that the electricity from EV, from the electricity for the EV is from renewables. Okay, so what technology is available for the urban and energy thermal use? So we identified, a number of those. I think Aalborg University and the professors from Aalborg University have covered quite a lot, and also in previous seminar we covered thermal direct use of thermal energy. And so I would just want to highlight a couple for this is here. It's first, I think the solar thermal applications, and is a very it's very common in cities, and starting from the water heaters and solar water heaters individual, and some more so gradually you can see that's at the building complex level. And so it's in some countries or cities it's become required, and part of a building code. Basically you need to have solar water heater, and for the entire building, multiple levels of buildings. So that's and for the hotels and for the commercials, they are more common simply for the economic reasons. So the technology and multiple, and I wouldn't get into very much details. You can see that there's evacuated tubes is more commonly used, and a flat plate as well, and a little less efficient. And so concentrating solar energy is also for heating is also becoming more and more popular in some cases. And I will talk about one case, later on. So that's just the direct thermal use. I think this is a very, very important. We have run the entire seminar in the past on this topic, and but I just want to maybe reiterate some highlights. Actually, for the reason why it's important, because it's almost accessible to all the cities anywhere. It depends on, of course, the quality is a bit different, but actually the resources available there, thanks to the actual heat pumps applications, the wide use. So you can, I think, that professor from Aalborg University already highlight that the heat pump play a critical role actually to scale up and applications of direct use of geothermal. Just to give you an example, how actually the magnitude from 2001 actually to 2018, there's 60% actually the applications of geothermal use has been increased been 60%, and basically mostly and thanks to the heat pumps and applications. So currently there's a total installed capacity for geothermal use, direct use, it's 107 gigawatt, and according to the International Geothermal Association's number. And we did actually map out the plant for the geothermal plant. That's globally. We find it out actually 60% of the installed capacity and near the cities and 50 kilometers in radius. So that's also very interesting and finding. We will see that how actually geothermal can be used for the cities. And heat pump we'll talk, there's not only the ground geothermal, but also actually there's other source heat source actually can be used, aquarium, the water body, and of course up to the regulations, and also with the air source as well. Heat pumps is becoming also important in those regions that's not so cold, because cold climate can cause some problem, but there are some designs and actually to address those problems. I don't want to get into details in here. And the bioenergy and the waste to energy is also very important. This is a sort of conventional renewable technologies used in cities. This is urban wood waste, and also the waste from the municipal solid waste, and you use mass burning to burn and or incineration, call it, and to generate heat, and can use for electricity and also district heating as well. And so this is being seen increasingly important in Europe, because they have the set of the directives actually by 2030, 90% reduction for in the landfills. So this is I think that we can see it more and more in the across the world, because the landfill capacity for garbage and becoming smaller and smaller. The last is, but not least, it's the surplus, renewable electricity for heating, and through circuit coupling technology. Heat pumps are very efficient. By electric boilers, we also see this in many countries and applications use electric boilers as well. So that's an area probably there's need of research to see how most effectively, and we can use the surplus renewable electricity and for the heating purpose with other technologies or innovations could help to make such a transition. And so building on that, so how actually to get the technology into the cities? Of course, urban energy planning is very important, and getting engaged with the municipals in terms of urban energy planning process as early as possible is critical. But another aspect is also equivalently important, which is how I could develop the project. and the district heating project, both the network and also the production as well, the heating and the cooling. And so this is for this purpose, we develop a technical guidelines and for heating and cooling system in cities. So basically, this is the help of the sector, different stakeholders, and to find development renewable source district heating and the cooling system, and how actually translate that concept into projects, concrete projects. So that's so we can we'll do the how from the identification of the project. This is what how do you identify the project, and at the very early stage, and to the screening, the project screening, and to different options, and you can identify multiple alternative options, and then how do you narrow down to the short list you want to actually zoom in to see the technical configurations, then you compare more technical and engineering levels. And also this is also helps to how to prepare and the development. So this is and also towards to the development options, the development potential options, technical options. And also this is will be help actually plan the networks and the urban district heating and cooling and networks. And so what need to be, how do you size that? How do you evaluate the demands, and also the what kind of supply resources available to meet that demand? And so that's how can be helpful. And this is step by step actually, and the technical guidelines. And so what on each steps, what critical questions and also process need to be taken into considerations. And for project developers, what kind of risks you need to assess carefully. So that's to give you some insights. This the guidelines is going to be published probably in like 2 months. So that's to say, and then it will be uploaded at the IRENA's website. And the technology, as I already mentioned, cover both technology, low temperature, and as well as networks as well. And so here's some takeaways. I don't want to get into detail, already mentioned. I'll skip over that. And now let me to move to the 2 case studies. First, we've done this is on China. This is called Zhangjiakou, and this is city, and also this is supported to the project supported by IKI. And so with that, thanks very much for the German government. And so the cities we're done with the municipal government for Zhangjiakou, and also this is a China Energy National Renewable Energy Center. We jointly conducted this project and study. So this city is very important in a sense. This is very close to Beijing, and this is by the state government actually appointed as this national renewable energy demonstration zone. So that means that the technology used and also the planning that will be replicated at least as a model and for the other city to look at. And also this is going to host the low carbon Winter Olympic 2022. And so this is relatively small and well, but in China, in the European size quite big. It's 4.4 million, but it's very cold actually in summer, winter time. This is a 5-month long heating period. And the heating system right now, this district heating is it's about 1/3. And the space and heating covered by district heating, and roughly around 1/3 by the boilers, but at the building compound complex level. So it's not regular, shorter, sort of smaller district heating system. Can put it that way. And here's but most of them, 95% actually currently, and the heat supplied by coal. And there are reasons for that. It's it's hard, as I think as Jack already mentioned. It's difficult to decarbon and the heating system. and currently it's mostly fueled by fossils. This is particular case in China, and so there's CHPs by coal-fired CHP, and there's also the boilers also with heat with coal power. So but they have the huge, very ambitious actual target to transform the heating supply of the cities. And because one of the reasons they have a huge amount of solar and wind potential. For the power system, there's no problem because they already reach roughly on 75% installed capacity and from the wind and the solar. So for the power sector, is that they have quite a well in advance, but for the heating, it's an issue and the challenge. Currently, they are set a target for 2020 and 2030, and for renewable energy shares in the total final energy consumption. So as you can see the chart on the right upper level, and so the district heating and basically the approach is pretty simple, and this is can they substitute coal and using the renewables. So the discussion and also with expert we come up with some options there, and some biomass they use some, and the geothermal they are exploring, and but the geothermal there's a little bit tricky in terms of regulatory regime. So this is areas it's also under actually some studies, and this is how can they break the regulatory and the regime, what the regulations need to be and change a little bit. Right now it's a gray area and still the projects going on, but might be there some in future there's some discussion around that. But I always see this only in favor of renewables and especially geothermals applications rather than becoming a barriers, regular barriers. And given the Chinese government, central government, huge ambition to transform the entire energy system into low carbons. And so for Zhangjiakou, there's surplus because as I mentioned, the power and the renewable energy electricity generation is huge, and so there's a huge potential. They are right now already applied quite a bit, and the surplus renewable electricity mainly from solar and wind for heating and through the electrical grid, and then using either heat pumps or electric boilers, and then with thermal energy storage, and then provide heat services to the consumers. So that's the way they do right now. And for directly use, as I mentioned, the biomass and geothermal could be the options. And one of the interesting thing is that they use it for concentrating solar thermal, and together develop a technology together developed with China Academy of Science and Make Design. It's quite an interesting project. They have the seasonal energy storage as well to provide as massive residential and compound. So that's also an interesting case. And next, for the Zhangjiakou, we developed the energy transformation strategy, and the local government they are going to take the key elements and to implement in their shorter term and energy planning. So that's a very positive and encouraging news. And the next case is Cyprus, and so they use also the parabolic trough collector, and for industry and steam use. This is we have this done by actually the Professor Kalaguru. This is from the university, separate University of Technology. And so I thank for the professor for providing such case studies. I think the key takeaway or element for this is that the concentrating solar thermal is conventional user generating power, and but gradually you can see increasing actually using for the thermal applications for industry, and it's industry energy use actually it's a little bit challenging currently, how we can decarbonize those that sector. So this could be the one of the option. And connecting to district heating and cooling is that the cascaded use of thermal energy. And because many industries actually they are not very far away from the cities, the urban areas. So the load actually can be there. So there's also discussions around the world how can link to the either constantly waste the heat and or the the new generations of heat source like from renewables and the power to decarbon industry and sectors. And then actually that we also need to be thinking in connection to the district heat and cooling for residential areas. And also another thing for this case study is they use concrete thermal energy storage, which is also is common. It's gradually you can see that more and more in the applications, and because of the economic profiles as a little bit cheaper. And but there's also need to more experiment in terms of performance and specifications, configurations need to be done. And this is just to show the system configuration and their capacity. This is a rather actually it's as the first of for those in Cyprus to use to test, and this is to provide and heat for the juice making the plant. And so the temperature they reach pretty high, but this for industry use, as I said, once used the heat become a lower temperature heat that can inject into the thermal to the district heating and networks. And the control system is also a critical part as well. How to optimize the operations of the system is also critical. And okay, with that, I thank you very much for your kind attention. As I mentioned, this presentation is based on 3 reports, and one it's already published, this online. The other 2 is going to be published in 2 months also. That's also will be uploaded on IRENA's website under the publication. And thank you very much for your attention once again, and I'll be happy to answer any questions raised by audience at a later stage. Jack, I will hand it over back to you. Thank you.
Thank you very much, Yong, for that presentation. We will do a very short question and answer session. And the first question that we're going to take, we're going to direct it to Jakob. And the question is asking, when we're using a 4th generation district heating system, and we have a process that requires higher water temperatures, which solution is feasible to use? Is it a heat pump or a water booster at a substation level at each of the households?
That's a good question. I think it depends on the specific, how high you need a temperature and how consistently you need it. If it's consistent and you can boost it with a heat pump, that's a very efficient technology to use. In some cases, if it's not all the time you need to boost it, or it's for a short period, then maybe an electric boiler is sufficient. And also, finally, if it's for some industrial processes, you might want to look at a direct electric boilers installed at the industry.
Sorry, it was a bit noisy, but we could hear it.
Sorry, my bad. I hope it's better now. I can just repeat. No, so it depends on the temperature and how long you need it for. If it's a very constant but not such a high boost, that maybe a heat pump is a very good solution. if it's for a very constant or short period of time where you don't want to have so high investment costs, then an electric boiler, water, so boosting it with that could be a better solution. And finally, if it's for industry and some processes, it might be smart just to simply install an electric boiler at the industry and use electricity to heat water there directly for the process, and then use waste heat actually in your district heating grid. So it depends a little.
Okay, thank you very much for that. And just a follow up to that question is what we can clearly see from your presentation is that retrofitting of the existing building is almost a necessity if you have to use the low temperature renewable energy sources for heating.
Yes, you need to do something like retrofitting, which become very important, at least with the equipment, and potentially also in definitely also in looking at what is the performance of your buildings right now.
Okay, thank you very much. So I see there are no more questions. So we will go to the next session where we are going to have a presentation being given by Mr. Alexander Richter. Mr. Richter is the Managing Director of the Renewable Energy Cluster of Iceland and the Iceland Geothermal. And this is a cluster initiative for Icelandic energy and geothermal sector. He's also the founder and editor of the Think Energy and the outgoing president of the International Geothermal Association, as well as a board member of the Canadian Geothermal Energy Association. And Mr. Richter's presentation is going to focus on, his presentation is going to give an overview of the energy market and the geothermal energy in Iceland. So, Mr. Richter, the floor is yours to give us your presentation.
Okay, sorry, I was not unmuted. Yeah, thank you very much for the opportunity to present you the story of the district heating in Iceland, naturally with a focus on geothermal. Maybe as a quick overview to put things a little bit into a perspective. The population of Iceland is about 360,000 people. So in the
we can't see your slides.
You can't see my slides?
No, I can't see them.
Okay, hang on. Then let's go and the.
Yes, now we see them.
You see it now?
Yes.
Okay, I apologize. So I start again. The size of the country is around 103,000 square kilometers and has about 360,000 people. So in the global context, it is a really small country. And in the context of geothermal and in the importance to the Icelandic community is important to state that in the electricity production, it only represents about 30%. So geothermal is really not that dominant in that context of electricity. Here, hydropower is the largest resource. But what is important to say is that geothermal power production in Iceland has been operating for the last 47 years. So it's a long history. And how are we using geothermal energy? So as I said, we've been producing power since 1969 from geothermal. And the overall installed power generation capacity today is around 755 megawatts, electric that is. Historically, Iceland, when it was discovered by the Vikings, around 870, it was immediately recognized the hot springs of the country. So we jokingly say that geothermal has been used in Iceland over the last 1,000 years. But if you look at the installed heat generation capacity in geothermal, it's around 2,100 megawatt thermal. So it shows you that this is much larger in the context of electricity production. And if you look at kind of how are we using geothermal energy, we see that electricity generation as part of the overall use of geothermal represents only around, or represents about 39%. And the rest basically is utilizing geothermal heat directly. And of that, space heating is the predominant part. The rest goes for heat use in swimming pools, snow melting, fish farming, greenhouses, and industry, and plays a really important role in the overall energy context of the country. And the importance is shown in this overview. It's not a fantastic graphic, but it shows you kind of the importance in the overall primary energy supply of Iceland. And you see that coal was a predominant source of energy in the 1940s, and then oil coming in very strongly. And then basically with the development of geothermal in the 60s and 70s, you've seen the increase in the utilization of geothermal and the importance of geothermal in the overall energy mix. And if you look at district heating in Iceland, it's all geothermal resources heated district heating systems. We have a large number of local district heating systems all over Iceland, all as to say actually most over all of Iceland. There are parts in the southeast part of Iceland that we have troubles kind of finding sufficient geothermal resources for district heating systems there. There are the efforts underway to utilize those, but most of the geothermal is centered around the southwest corner of Iceland and then all across the country. And the impact district heating and geothermal district heating has for some of these communities is quite important. Because in the past, a lot of these local communities were heated by electricity, and with the weather conditions in Iceland in the wintertime, sometimes there will be power outs, and the problem there is that you didn't have heating. And naturally, electricity or heating by electricity is also quite pricey. So utilizing geothermal in those communities has changed their lives dramatically when geothermal was drilled and these district heating systems set up. Reykjavik as the capital of Iceland, and the Reykjavik area represents about 200,000 people, so a predominant part of the country. And it's today supplied by around 1,100 megawatt thermal capacity. And the history goes back to the early 1900s when in Reykjavik, so the Smoky Bay in English, and part of the outside of the city were hot springs, which have been used by local women for doing laundry. And these hot springs with the spreading city are now within the perimeters of the city itself. So if you look at the history of geothermal district heating in Iceland, it is, as always, innovators play an important part. And in 1908, there was a farmer that had a hot spring on his property, and he piped the geothermal water from the hot spring into his house. And that was basically the first recorded heating from geothermal in Iceland. And then in the 1930s, shallow wells were drilled in the vicinity of those hot springs that I mentioned earlier, with water of about 90 degrees Celsius. And then 3 kilometers long transmission lines were put from those hot springs towards the town center at the time. connecting a primary school, secondary school, swimming pool, and about 60 to 70 houses. And that essentially was the start of the district heating in Iceland as we know it today. So today, we celebrate 90 years of geothermal district heating in Iceland. And then based on that, things picked up quite a bit. So in 1943, an additional field within the city parameters was utilized for geothermal. Shallow wells were drilled with, again, around 90 degrees hot water, and a 17-kilometer long transmission pipeline piping running into the city, and at that time heating around 2,800 houses. This is the secondary school that I mentioned earlier that was connected in the 1930s, and that was a big change in Iceland. And in the 1940s, Iceland was still utilizing a lot of peat and coal to heat, and the smog over the city has always been an issue. And actually, this has changed dramatically by utilization of geothermal energy. And development continued throughout the 40s and 50s. And then in 1970, all houses in Reykjavik were connected with the district heating. And the capacity that was increased from the two areas used to feed the district heating system. And with the growing demand, there was a look at going beyond these relatively low temperature wells in the perimeter of the city, and the development of the first big geothermal power plant at Nesjavellir, which is about 30 kilometers from Iceland, from Reykjavik. And it was set up as a combined heat and power plant. And that was a first step in Iceland where the water, the hot water from high temperature field was utilized to generate electricity. And after the use in the power plant kind of was sufficiently hot to be piped to the city of Reykjavik. And today, with about 27-kilometer piping system fueling into the district heating system that is fed by both high temperature resources and lower temperature resources. In 2005, another combined heat and power plant was set up about 30 kilometers from Reykjavik that today also provides some of the heating in the city. So today, the Reykjavik district heating system, feeding heating to around 200,000 people, is among the largest in the world. And actually, with development in China and so on, there will be definitely changes to that, but it's still like the largest geothermal and combined geothermal district heating system. And it derives heat from the combined heat and power plants, but still today around, I would say about 70% at least is provided by lower temperature water resources in the vicinity of the city of Reykjavik. Providing around 2,400 liters per second of about 60 to 130 degrees hot water. And I understand that this would not be considered low temperature in some geographics. So here you have an overview of how the geothermal district heating systems were gradually developed. You see the red houses here in Reykjavik, which were the first houses heated by geothermal, and then gradually expanding. And the purple here is the downtown area of Reykjavik, and then gradually expanding beyond that, and with new developments, then the blue and the orange or brownish areas as well. So here an overview over the sources where the hot water coming from for the systems. And we have the Laugarnes geothermal field, which is where the local swimming pool is and the football stadium of Reykjavik. Here you have about 10 exploitation wells with a temperature of about 120 degrees Celsius. You have another area here, Aalborg, which is like a little creek that runs through the city. There, about 8 wells have been drilled, providing around 50 megawatts of thermal capacity. Then you have the larger field at Reykja and Reykjavik, which is about 90 degrees Celsius water, capacity of around 2,000 liters per second, so quite important. About 34 wells drilled here. And then you have the 2 high temperature fields of Nesjavellir and Hellisheiði, here combined heat and power plants, both utilizing around 83 degrees Celsius water. Here there is excess water from after it has been used to generate electricity. And the overall number here of these 2 plants is around 65 to 70 wells. Naturally here in that context of district heating, to be considered that this is also providing a power plant. Part of the hot water that feeds the city is pumped in 2 or 3 tank systems above the city. Here it's one that has been rebuilt to a tourist attraction above the city of Reykjavik. But these piping or these tanks have played less of a role in recent years. So some of these tanks actually are not full anymore, but they provide the city with hot water as well as a backup. And to show you how this looks like, so this is the Laugarnes area, which was the first area that was utilized for geothermal district heating. And here you have the wells that are set up within the city, and you hardly see them. And these wells were drilled when there were no houses there, so I have to admit that. It would be interesting to see if there will be new wells to be drilled there, but some of these wells here have been operating for 50, 60 years. And they're feeding into the district heating system. This is how it looks like. So this is one of those wells, picture taken on a February day, and people would not recognize this unless they would see this little steam coming out here. This on the right, you see the pump that is pumping the hot water within that well housing here. And what has been really interesting is the development of the know-how of these wells. So starting with shallow wells, about 200-300 meters, these wells are now a depth of around 1,000 meters, and a lot of the pumps, etc., kind of like did not exist at the time. So the challenge was how to deal with the temperature in these pumps. So all of this development basically happened over the years by some really innovative people within the companies that are developing these systems, and it's a very interesting story. This shows you one of the combined heat and power plants here at Hellisheiði. In the background, you see Reykjavik, and you have piping running from that plant all the way to Reykjavik. As a background of how was this made possible, it was very clear is that the drilling was a challenge. So in the 1960s, the government set up a geothermal fund which is now named the National Energy Fund. And here the idea was to provide low interest loans to municipalities to help them get off with the drilling, to use in horticulture or similar for heating homes, etc. And here is that the state actually takes on part of the risk undertaken by the developer. And the developer in this case was the city utility of Reykjavik, which is now called Reykjavik Energy. It's a merger of several different companies combined, but essentially it was owned by the local utility, and a lot of the funds were made available for some drilling, for example, in greenhouse areas, etc., that are either owned by private players or communities to supply the local community. So the loans that were provided under, or that are provided under the fund, normally cover around 60% of the total drilling cost. But in later stages, that included also grant support of up to 50%, and here mainly for exploratory activities. And this fund has been really fundamental in helping Iceland develop its geothermal resources. The research was done mostly by the National Energy Authority, with a lot of the geological and geoscientist research done within the authority to help support communities and developers in their activities. In the 1940s, and actually to push geothermal, a state drilling company was established, which was then privatized in the late 1980s. Today you have the company still exists. It's now privately owned, but it's focused on high heat drilling in Iceland and internationally. There are several small drillers that are focused on lower heat and shallow drilling for heating projects across Iceland. The Geoscience Department, which was part of National Energy Authority, was a spin out of the authority in 2003, which is today Iceland Geosurvey, or ESOR, as the agency that is supporting the energy companies of Iceland and developers in their activities on geothermal development and resource management. The economic savings for Iceland through geothermal are tremendous and have played an important part overall in the economic well-being of the country. So in 2010, the Energy Authority actually did a study to look at kind of what are the accumulated savings. So over 40 years from 79 to 2008, it was estimated that around about $10 billion have been saved. And that's around 3 times the Icelandic budget. And the estimated oil savings overall are around $22 billion over the same time period. So if you look at the economic benefits to the country from geothermal in 2010, there was the study that was released in 2013-14, is seen around between $480 and $800 million a year. That represents about 4 to 6% of GDP of Iceland. That includes naturally benefits of the space heating and other industry-related benefits and impacts. So geothermal really plays economically an important part of Iceland. There's another impact that is, I guess, more related to how individuals and people in the country kind of are surviving or benefit from geothermal. And this was a study was done by the Samorka in Iceland, looking at the district heating cost in the Nordic countries in Europe. And that shows kind of like how geothermal and the setup in Reykjavik provides very, very low cost for individuals to heat their homes. And it shows the importance and the savings just for the individuals on a monthly or yearly basis. And the excess water from the district heating actually heats then also in the what we call cascaded use, also streets to keep them ice-free here in downtown Reykjavik, the piping that runs under the street to keep the streets ice-free. And closing off, I want to kind of give you an idea of some of the work of Icelandic companies internationally. And here, I guess, in the Chinese context, a joint venture that was established in 2006 with Icelandic participation and the largest oil company in the world, Sinopec, in the establishment of Sinopec Green Energy, which is today the largest and fastest growing geothermal heating company. I think they've drilled over 500 wells so far, purely focused on district heating. And today supplying geothermal heating in about 48 cities and counties with about 40 million square meters in space heated by geothermal. And it's a huge impact, and it's still owned partly by an Icelandic company. So this is a success story of the export of the Icelandic know-how as an example. And with that, I want to thank for your attention and looking forward to answer any question that you might have.
Thank you very much, Alex, for that enlightening presentation about how Iceland has managed to become the leader in district heating. And just before we let you off the mic, just to ask a follow-up question to your presentation, we see that geothermal is usually a resource that is suffers from a lot of negative publicity. I mean, negative perception. But Iceland has managed to overcome that and get to the level where most of the buildings right now are heated using geothermal. So what are some of the lessons that we can learn from the Icelandic experience, which can be replicated in other areas?
I think what we have to admit in Iceland is that a lot of the early stage drilling for the district heating was done before the houses that now surround these wells exist. So it's easy to say that this is totally socially accepted. And today, most of the drilling that happens, for example, with the power plant, happens outside of the city. There have been some complaints with regards to smell and let's see, seismic events from re-injection. So it is a constant. It's a constant issue that we face as a geothermal industry, is to talk about geothermal, talk about the benefits, and maybe accept some of the temporary challenges that we face with regards to noise in the case of drilling, etc. But I think there's an overall understanding is the benefits of what geothermal provides to Iceland. I mean, you just need to see the swimming pools that are open year round and are open for people to enjoy geothermal. But we need to constantly talk about the benefits of geothermal for people to understand that what is required to do this. And this is, we have to admit, a constant struggle that we have here in Iceland as well. We need to constantly talk about the benefits of geothermal in order for people to accept some of the activities that are required to make geothermal work. So that is very important. And in the case of drilling, really, it is the advantage for us. It's that the Iceland is not that populated, so it doesn't happen so close to people's homes. So we have been fortunate in that regard. And there is also in Iceland opposition, we have to admit, to some of the high industrial development. But the impact that geothermal has and the benefits it has, for example, with local food production, etc., this is a constant story that we need to tell and re-emphasize on a constant basis for people to accept geothermal and the opportunities it provides.
Thank you very much for the comprehensive response. So at this stage, we will go to our final presentation. And this presentation will be given by Mr. Olivier Hako. Mr. Hako is the Director for District Heating and Cooling at ENGIE, and his work involves creating centers of excellence in district energy systems and ensuring the deployment of ENGIE strategy by implementing decentralized and decarbonized solutions. So at this stage, I'm going to ask Mr. Hako to give us his presentation, which will be focusing on the role of district cooling in accelerating decarbonization. So, Mr. Hako, the floor is yours.
Thanks a lot. Jack, can you see my screen?
Yes, I can see it.
So thanks a lot for inviting me to be part of the panel. I'm gonna be very short since we have very few minutes left. I will be focusing on district cooling since lots of already heating system have been covered during the seminar. So I'm part of NG, and as said by Jack, I'm in charge of the development of district heating and cooling systems worldwide. And our belief is that those systems could bring lots of benefits to territories and cities in decarbonizing those cities. Let me give you some very high-level figures around cities and what is the current trend in terms of cooling. As you said, most of the CO2 emissions are related to cities, where in the future most of the people are going to live, since 70% of the population is expected to be living in cities in the future. And what we can see right now is that there is a need for reducing the energy consumption, but as well for the GHG emission and CO2 emission related to heating and cooling. And what we have seen very recently in the past is that between 1990 and 2016, the cooling demand tripled. And at the same time, the CO2 emission related to cooling, to space cooling, tripled as well. And you can see on the slide that the cooling demand is expected to be growing in the future, again to triple once again. So we have to focus on cooling, and we have to focus on energy efficiency, as that has been mentioned during the webinar. When we meet with decision makers, and when we have a chat with them in order to better understand what are the key drivers or the key concerns that lead them in order to implement the district systems, either heating or cooling, every time the reply is more or less what you see on the screen right now. It's first we have to focus on energy efficiency in order to reduce the energy consumption. Then we have to focus on CO2 reduction, and then we have to, as much as possible, to introduce renewable and local energy in order to feed the system and in order to reduce the GHG emission and CO2 emission. Some of the concerns that are very important in the discussion that we have with city mayors or any kind of authorities or decision makers is that we have to guarantee some financial budget and savings, but as well to be really focused on the end users. This has been developed during the seminar, the webinar, but we have to focus on the satisfaction on the end user and to get the end users involved and maybe to raise a little bit the awareness about district and heating system and cooling system and about the benefits of those systems and the benefit that those systems can bring to a city. Integration of those systems in the city, as mentioned in Iceland, for instance, it's very important for us, since those systems are supposed to be developed in dense areas, so within cities. So we have to figure out how to integrate those systems within a city in respect of and with respect to the architectural integration, or maybe to the history of the city. And another concern is also a nature-based solution. Very often, right now, cities are concerned about the fact to reintroduce, if I can say that, the nature within a city. So why it is important for cities to work on those systems? Once again, the first topic is really to consume less resources, and less resources can be local resources, but as well gas or fossil fuel resources. But really the first concern is to work on the energy efficiency in order to be able to reduce the energy consumption, but as well the water consumption, chemical products consumption, and to reduce the operating maintenance costs in order to be more and more competitive and to reduce the energy bills for the end users. And then the second focus is really to shift from fossil fuel to green energy. Doing so, what what we do and what we do foresee right now is that the concern is more and more local. So all the solutions are more and more local, and really the focus is right now on promoting the circular economy, which means try to benefit from local resources such as geothermal, but as well excess of heat that may exist within a city or territory in order to feed a system like a district heating or a district cooling system. And the second focus is to have a dedicated focus on coupling sector and on synergies among the different sectors. And I'm talking about power, heat, and cold. And again, all this is really to improve the safety and redundancy of the system, to maximize as much as possible the recourse to green energy and renewables, or maybe excess of it that may exist in cities, and to reduce as much as possible the pollutions and the CO2 emission, but as well the noise pollution created by, let's say, cooling towers that could exist on the rooftop of building, albeit as well the visual pollution of lots of windows that could be existing in the facade of a building, by replacing them or removing them thanks to a district cooling system. And the last point really is ready to embark the people and to get involved the people thanks to visits, to webinars like this one, in order to raise the citizen awareness about the system and the benefits of the system. So how we can do that? We have been talking during the webinar about lots of existing technology. To be clear with you, the technology might not be problematic right now to implement a district cooling system. We have been talking about chillers or compression chillers, but as well heat pumps or absorption chillers. And we have been talking about the use of free cooling that may exist if you have a city which is located close by to a river, a lake, or maybe a sea. So you have existing technologies that can be applied to create and to implement either a brownfield district cooling system or a greenfield district cooling system within a city, and in order again to benefit and to promote the circular economy and the recourse to local resources to create local jobs, in order to favor the social economy and the social acceptance of the citizen for such technologies. To do that, and this is something that we discussed during the seminar, and this is something you're gonna find in the guidebook you're gonna issue. The real first thing is really to work on the planning. For this, we developed a set of tools in order to come up with urban planification or energy management planification, and in order to work with cities in order to figure out what would be the best solution in terms of district cooling, and what could be the layout of the district cooling within a city in order to connect as much as possible the number of buildings in order to maximize the benefits of those systems. So we have been developing a set of tools in order to come up with a urban planification, but as well in order to better optimize or to better operate our system in order to guarantee the energy efficiency and the competitiveness of our system. This is a kind of tool that I was talking about. What is critical for those systems is that those systems are capex intensive upfront. So if you want to be able to benefit from those systems, you will have to create or to find the critical mass in terms of connected building to the system in order to justify the investment and to make it economically viable. So here again, the urban planification is key. So we have been developing a tool where we are able to cross some data regarding the cooling demand, regarding the urban density, regarding the local potential, so local potential in terms of shallow or deep geothermal, biomass, solar, but as well excess of heat that may exist within a territory, in order to come up with the best solution in order to develop a district cooling within a city, again, according to the local specificity of that city, and to what could be existing in order to be as much as possible competitive, but to recourse as much as possible, or to favor as much as possible renewable energy. So I'm gonna go through very quickly right now through 4 different business cases which are existing to be reviewed and where different technology have been applied. So the first one is the Clean Espace district cooling system in Paris. So this is a district cooling system that started out in 1991 by one customer to be reviewed, and right now we have more almost 700 customers connected to the system with 10 different cooling plants. And the specificity of that cooling system is that we are benefiting from the free cooling coming from the Seine River within Paris, since 3 of the power plants are connected to the Seine River in order to chill and to feed the network and to chill the condensation of the chillers when the temperature of the Seine River is a little bit higher. This leads to a better energy efficiency, to less water consumption, to less chemical product consumption, and to less CO2 emission compared to a standard solution. In addition, for that system, all the electricity, all the power needed to power the chillers or the pumps is coming from a green PPA, coming from a hydro facility in the south of France. The next case is the London Olympic Park in London. So this is a network that has been developed for the Olympic Games in 2012. And the specificity of that one is that we are generating power, and at the same time we are producing heat and cold for the territory which is nearby the network. So we distribute heat and cold to the city, as well as power to the neighborhoods. And you can see the capacity installed for each of the facility, cooling and heating. And we are using, in that case, biomass in order to produce heat. And while we are producing heat, we are benefiting from the excess of heat in order to produce chilled water thanks to absorption chillers. And in addition of that, we are using as well thermal storage. But the specificity of that contract is that we are already, in the frame of what we call the sector coupling. So we are generating power, producing heat, and producing cold. The next one is a network located in Barcelona in Spain. And for that network, once again, we are producing heat and cold at the same time. And for that network, we are benefiting from waste heat coming from a waste to energy system located nearby the main central plant. And thanks to that waste heat, we are producing cold thanks to absorption chillers. And we are producing heat for the city. In addition, we are using seawater in order to use, depending on the temperature, to use the cold coming from the sea in order to feed the network for cooling for the cooling system. Here again, the benefits of that set of technology, if I can say that, leads to less fossil fuel consumption, less water consumption, less chemical products, less GHG emission, And once again, we are talking about interoperability of the system, since we are producing heat and cold at the same time, thanks to waste energy that wouldn't be used if the district cooling system wouldn't be existing. And the last one, very, very quickly, is a new district cooling system implemented in the south of France in Marseille in 2008 and commissioned or completed in 2010, if I recall correctly. And this system is connected to the seawater, and thanks to that seawater loop connected to heat pumps, we are producing heat and cold for the neighborhoods, and we are delivering the heat and the cold throughout a network which has been implemented in a new urban area created from scratch with the city. And the intent is really to accompany, if I can tell that, the development of that area, and to provide to our customer green energy. And once again, the technology used leads to less electricity consumption, less GHG emission, less water use, and less chemical products. So for all those cases, you have seen that we are using different technology. All those technology are existing, applicable almost everywhere. So the technology is ready in order to deploy or to implement district cooling system. And for the last minute that I have, if we had maybe one or two recommendations to unlock the district cooling potential, is really to focus on the business model that are needed right now in order to maybe to take into account the benefits of those systems. We have been talking about lots of different things, you know, less water consumption, chemical products, less CO2 emission, GHG emission, but as well reduction of the pollution, either noise pollution or maybe visual pollution, or as well air quality within cities. All those benefits right now are not part of the business model. So what we try to do, we try to promote a new business model in order to take into account all those benefits, which are very important for citizens, but as well for decision makers in cities. And maybe the last one is really to focus on a systemic approach, if I can say that, and for future system, not only to consider cooling or heating or power, but really to focus on what we call the sector grouping, or the integration of the different systems, in order to benefit and to maybe to benefit from the excess of power generating by wind power farm, solar farm, in order to maybe to power the heat pumps, the boilers, the chillers of a district cooling, and to produce in the same time cooling and heating, as well as power, thanks to heat pumps, thanks to engines, and thanks to new technology in the future of storage. We do believe that the integration of all those systems will be possible. This will lead to, again, even more efficiency and less GHG emission and less CO2 emission. And those systems, thanks to that kind of integration, will become more and more competitive, and will create a social economy, and will be at the heart of the development of the future cities. I think I'm done. Sorry for that. It's been a bit long, but I think I'm done.
Thank you very much, Olivier, for that very nice presentation. Actually, we've been getting a lot of questions from participants asking when we are going to talk about district cooling, because some regions are more suited for district cooling than for district heating. And one of the questions that we've been getting from our participants from from the MENA region and from Southeast Asia is what are some of the options that are available for district cooling? And for example, how can we use shallow geothermal in cooling? And is this a technology that has developed that is mature? And what are some of the trends that you're seeing with regard to the development of this technology as a cooling option?
So good question. Yes, geothermal solution is definitively a solution to be coupled with district cooling systems. And you know what I'm referring to free cooling, I was talking about the river, the lake, and the sea, but you can connect heat pumps with borehole systems in order to produce heat and cold at the same time. And this is already existing in the Netherlands, for instance, in the UK as well, in France as well. So we are already connecting, district cooling system with borehole systems, but as well with aquifer thermal storage. So using some reservoir or aquifers in order to produce heat and cold at the same time. And this kind of solution maybe also we can also connect a deep geothermal solution to a district cooling system, to be clear with you. So if you have an aquifer underneath, we could benefit from the aquifer and we could produce thanks to heat pumps. We could produce heat and cold at the same time. And again, those solutions are already existing, and those solutions are already deployed in some region so far, mainly in Europe. You're correct, but let me guess that in the future, this is going to be the case in the Middle East as well.
Okay, thank you very much for the response. We also have a question here. I think this is directed to the Aalborg University, and the question is: when you're dealing with the seasonal behavior of some of the renewable energy sources, how do you handle these using the so-called prosumer models? Maybe Jakob or Brian, you can assist to answer this question.
Yeah, sure, I can take that. This is Brian. It's a very good question. The seasonal variety is there for a lot of the sources, and when you have the thermal grids, you have to have a robust mix of sources. You also have to have an energy storage or a thermal storage, or that at least that is a good thing to have. A thermal storage will provide you with flexibility between maybe 2-3 hours and 10 hours, and this means that you have flexibility towards some of the renewable sources. When you have seasonal variety, you have to construct the mix of district heating supply in a way that you're able to flexibly supply this to the citizens. And the question here was also related to this prosumer idea. In our research, when we look at heating, it's actually more important for consumers or citizens to save energy than to move around the demand. Because if you imagine when it's really cold, it's cold everywhere. And in that case, it's the system that needs to flexibly adapt, and the individual cannot really adapt very well. So the best thing you can do as a citizen or a consumer is to use less energy.
Thank you, Brian, for that very nice response. I'll take another question here for Mr. Young, and the question is: we've seen how the collaboration between the national government and the municipality has resulted in the development of a strategy for decarbonization in Janjaku. What lessons can be drawn from this collaboration which can be replicated in other countries? on how to do this collaboration between the two levels of government.
Yeah. Okay. Yeah. Thank you. It's a very interesting question, and actually, it's not. Yeah, as you mentioned, as the question is about. Actually, it's not only the China. It's actually the rest of the world. There's the national government and the local government. I think the key thing here is that in the current energy systems, and it's designed and by more at the national level, sort of, because since after you debundled, the separate generation and the grid systems, especially you create competitions, it's becoming more a national planning, more related and exercise. But gradually, when we see that more and more renewables getting into the cities, and especially distributed generation, including the power and the heating actually, and cooling is more localized because of the pipelines. But the ownership can be different of the company, of course. So there's a planning process. It's need to be two ways, and the top down and the bottom up. So this is why actually we are engaging with the local government and to create a long-term and energy transformation strategy, because without the active engagement and participation from the local government, it's difficult for the national authority and to implement effectively their long-term vision. So this is of course, this is not an easy task, and because the different interests can be a little bit different, or priorities at different levels. So I think there's a need to be more dialogues between the national and the local government in terms of how actually they can plan and jointly and collaboratively. And in China currently, there's, as probably you notice, and there's this new way of planning, and more like at a regional level. So several provinces or several cities, they have to jointly develop their coordinated development plan. So this is a new shift in terms of planning process that's in China, because China before is used to be a national and then province-based planning, but now they expand to the several provinces in a coordinated way. I think this is can be applicable to the other countries. The way we see is you need to actually more at the city level to figure out how actually you want to transform your energy system to get yourself prepared for the future, not only for the supply, but also for the supply of energy, but also for how actually deal with the climate change that have increasingly negative impact at the city level. But thank you for the question.
Thank you very much, Yong. Well, we have two last questions, and the first of the last questions will go to Aalborg University, and it's about some places where it's not possible to use the locally available resources such as geothermal for various reasons, and also technologies like solar thermal are not widely spread in most countries. And the question is, what are the options that are available for such countries?
Yes, thank you for the question. So of course it would be nice if you have access to solar thermal or geothermal or some resource in that way. But else, of course, if you want renewable energy in your district heating grid, then the main alternative, and also what a large part of the Aalborg plan we presented is based on, is that you have some kind of a heat pump or similar that can boost, that can use wind energy or solar power or some other renewable source, electricity source, and convert that into heating.
And of course, and that makes sense, especially if you can combine it with a thermal storage. I didn't have time to show it, but a thermal storage compared to, for instance, an electricity storage is very cheaper. So here it could make a lot of sense to store the thermal storage when you have a lot of wind or solar or some other renewable electricity source, and then store it as heat instead, and then use it in combination with your district heating grid. So I would say that is one of the primary options when going to a renewable heating system.
Thank you very much for that, Jacob. And to the last question, this will be directed to Olivier. And the question is, when you're considering large-scale heat pumps for district cooling, is there a minimum runtime, e.g. the number of operating hours that need to be considered in order for the heat pump to become effective in the system?
Yeah, thank you for the question. So I don't have a specific figure to provide you, but you're totally correct saying that the main point is really to run the heat pumps at the highest possible efficiency. So it really depends on the demand and the weather condition where we want to apply those heat pumps. For instance, if I have to give a year, near Paris, we have several heat pumps connected to deep geothermal solution, and those heat pumps are running almost something between 5,000 hours and 6,000 hours a year. And again, connected to a base load, which is geothermal, and on top of that, we have additional means in order to meet the peak demand. But there is no golden rule to reply to the question. The golden rule is to run the system at the highest efficiency as possible.
Okay, thank you very much, Olivier, for your response. And now we are going to come to the end of our webinar, which also marks the end of our series of 3 webinars. And our next step will be to publish the guidebook for district heating and cooling. And this guidebook will be made publicly available on our channels, and it will be, you can download it from there and use it for various purposes. In the coming weeks, we shall also be contacting some of you to with regard to the guidebook, in terms of making a contribution and giving guidance on developing a few topics for the guidebook. Then later, as it was announced by Mr. Gulbuz Gonul, we are going to proceed with capacity building in other areas, for example, in China and in Central Asia. And we'll be reaching out to some of you to partner with us in these capacity building activities. And at this stage, I would like to thank you very much for your time and for your active participation in this webinar. And I would ask you, as you exit from the GoToWebinar application, please take a few minutes to respond to the survey, just to give us your views and your thoughts on what you think about this webinar. So ladies and gentlemen, we've come to the end, and I thank you very much.